Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Volcanic forces shaping the solar system, from fiery peaks to icy plumes. Volcanism is one of the most dynamic and transformative geological processes in the solar system, shaping the surfaces and atmospheres of planets, moons, and even smaller celestial bodies. This phenomenon, driven by internal heat and pressure, manifests in various forms, from the fiery eruptions of molten rock to the icy geysers of distant moons. Exploring volcanism across the solar system reveals not only the diversity of planetary processes but also the fundamental mechanisms that drive geological activity in vastly different environments. The story of volcanism begins with internal heat, the lifeblood of planetary activity. On terrestrial planets like Earth, Venus, and Mars, this heat originates from the decay of radioactive elements, residual energy from planetary formation, and, in some cases, gravitational interactions. This heat generates magma beneath the surface, which rises to create volcanic eruptions. On icy moons, a different type of volcanism, cryovolcanism, occurs when subsurface oceans or liquid layers are expelled through the icy crust, driven by tidal forces or internal pressure. Regardless of the medium, rock or ice, volcanism plays a critical role in shaping landscapes, altering atmospheres, and influencing the potential for habitability. Earth's volcanism, while well studied, serves as the foundation for understanding volcanic processes elsewhere. On Earth, volcanoes are primarily driven by plate tectonics, where the movement of crustal plates creates hotspots, rift zones, and subduction zones that allow magma to reach the surface. Iconic volcanoes like Mount Etna, Mount St. Helens, and Kilauea illustrate the power and complexity of these processes. Beyond Earth, however, the mechanisms of volcanism can differ significantly, offering a glimpse into the diversity of geological activity across the solar system. Mars, the red planet, is home to some of the largest volcanic structures ever discovered. Olympus Mons, a shield volcano towering over 21 kilometers high, stands as a testament to the planet's ancient volcanic activity. This massive structure, formed by repeated eruptions of basaltic lava, is the result of Mars' lack of plate tectonics. Unlike Earth, where moving plates create chains of smaller volcanoes, Mars' stationary crust allows individual volcanic hotspots to build up over time, creating immense structures. Though Mars is no longer volcanically active, its ancient lava flows and volcanic plains suggest a time when eruptions were common, potentially releasing gases that contributed to the planet's once thicker atmosphere. Venus, Earth's sister planet in terms of size and composition, offers a contrasting picture of volcanism. The planet's surface is dominated by vast volcanic plains, shield volcanoes, and lava channels that stretch for hundreds of kilometers. Venus lacks plate tectonics but experiences intense volcanic activity driven by the slow cooling of its interior and a thick, insulating atmosphere. Observations from missions like Magellan and Venus Express suggest that some volcanoes on Venus may still be active today, contributing to fluctuations in atmospheric sulfur dioxide levels. The extreme heat and pressure on Venus make direct exploration challenging, but its volcanic features provide critical insights into how a planet's interior and surface interact under harsh conditions. In the outer solar system, volcanism takes on entirely different forms. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes ejecting sulfur and silicate materials into space. This activity is driven by tidal heating, a process where gravitational interactions with Jupiter and its neighboring moons create intense friction within Io's interior. The resulting heat powers eruptions that shape Io's vibrant and ever-changing surface. The colorful deposits of sulfur and the towering volcanic plumes on Io showcase the unique dynamics of tidal-driven volcanism, offering a stark contrast to the basaltic eruptions seen on terrestrial planets. As we expand our exploration of the solar system, the study of volcanism becomes a key avenue for understanding planetary evolution and habitability. Each planet or moon with volcanic activity offers a unique perspective on the forces that shape celestial bodies, from the fiery eruptions of rocky worlds to the icy geysers of distant moons. Volcanism in the outer solar system reveals a fascinating diversity of geological activity, especially in the form of cryovolcanism, volcanic processes involving the eruption of water, ammonia, methane, or other volatile substances instead of molten rock. This form of volcanism is most commonly found on icy moons orbiting the gas giants, where extreme cold and unique gravitational interactions create conditions distinct from those on terrestrial planets. The study of cryovolcanism not only broadens our understanding of volcanism as a planetary process but also offers intriguing clues about the potential for habitability on these distant worlds. One of the most compelling examples of cryovolcanism can be found on Europa, one of Jupiter's largest moons. Beneath its thick ice shell lies a subsurface ocean kept liquid by tidal heating, a process generated by gravitational interactions with Jupiter and neighboring moons. Cryovolcanic activity on Europa occurs when this subsurface water breaches the icy surface, forming plumes that eject water vapor and particles into space. Observations from the Galileo spacecraft and the Hubble Space Telescope have confirmed these plumes, suggesting that Europa's ocean interacts with the surface, creating a dynamic and active environment. This interaction raises the possibility that chemical exchanges between the ocean and surface could support microbial life, making Europa a prime target for future missions like NASA's Europa Clipper. Another fascinating cryovolcanic world is Saturn's moon Enceladus, which has captivated scientists with its dramatic plumes of water vapor and ice particles erupting from fractures near its south pole, known as tiger stripes. These plumes are powered by tidal heating and originate from a subsurface ocean beneath the moon's icy crust. Analysis of the plumes by the Cassini spacecraft revealed the presence of organic compounds, salts, and hydrogen, key ingredients for life. Enceladus cryovolcanic activity not only shapes its surface but also feeds material into Saturn's E-ring, demonstrating how volcanic processes on moons can influence the broader planetary system. The potential for life in Enceladus ocean makes it another priority for astrobiological exploration. Triton, Neptune's largest moon, adds another dimension to our understanding of cryovolcanism. Unlike Europa and Enceladus, Triton's cryovolcanic activity is likely driven by seasonal heating from the sun rather than tidal forces. Observations from the Voyager 2 spacecraft revealed active geysers on Triton's surface, ejecting nitrogen gas mixed with dust and other particles. These eruptions, fueled by the sublimation of volatile ices, create dark streaks on the Moon's surface and contribute to its thin nitrogen atmosphere. Triton's retrograde orbit and unique surface features suggest a complex geological history, with cryovolcanism playing a central role in shaping its landscape. Beyond moons, cryovolcanism may also occur on dwarf planets like Pluto and Ceres. On Pluto, data from NASA's New Horizons mission revealed large, dome-like structures that could be cryovolcanoes, potentially formed by the slow extrusion of icy material from the interior. These features, along with evidence of flowing nitrogen ice and volatile transport, indicate that Pluto remains geologically active despite its distance from the Sun. Similarly, observations of Ceres by NASA's Dawn mission identified a cryovolcanic feature known as Ahanemons, a solitary ice-rich dome thought to be the result of subsurface brine erupting onto the surface. These discoveries challenge traditional views of volcanic activity, showing that even small and distant bodies can host active geology. The implications of cryovolcanism extend far beyond surface features. By bringing material from subsurface oceans or reservoirs to the surface, cryovolcanism provides a window into the interior composition and processes of these worlds. It also creates opportunities to sample and analyze materials that may contain clues about potential habitability. For example, missions to Europa or Enceladus could directly study plume material to search for signs of life or prebiotic chemistry, bypassing the need to drill through thick ice layers. Volcanism, in its many forms, plays a crucial role in shaping the solar system's landscapes, atmospheres, and even the potential for life. Whether it manifests as fiery eruptions of molten rock on terrestrial planets or as icy geysers on distant moons, this dynamic geological process is a key driver of planetary evolution. By studying volcanism across the solar system, we not only gain insight into the internal workings of planets and moons but also uncover connections between geological activity and broader astrobiological possibilities. One of the most significant contributions of volcanism is its influence on planetary atmospheres. On terrestrial planets like Earth, volcanic eruptions release gases such as water vapor, carbon dioxide, and sulfur dioxide, which can contribute to the formation and evolution of an atmosphere. In Earth's early history, volcanic outgassing was likely responsible for delivering much of the water and gases that formed the primordial atmosphere and oceans. Similarly, on Venus, intense volcanic activity has played a major role in shaping its thick, carbon dioxide-rich atmosphere, driving a runaway greenhouse effect that makes the planet one of the hottest in the solar system. Volcanism also has profound implications for the potential habitability of planetary bodies. By bringing subsurface materials to the surface, volcanic activity facilitates the exchange of energy and nutrients, creating environments where life might emerge or thrive. On Earth, hydrothermal vents associated with underwater volcanic activity are home to thriving ecosystems that rely on chemical energy rather than sunlight. This raises the possibility that similar environments might exist in the subsurface oceans of Europa, Enceladus, or other icy moons, where cryovolcanism connects the interior ocean to the surface and beyond. The presence of organic molecules in the plumes of Enceladus further supports this idea, highlighting the Moon as a prime candidate for the search for extraterrestrial life. Volcanism also shapes the long-term evolution of planetary bodies. On Mars, The vast lava plains and towering shield volcanoes like Olympus Mons provide evidence of a once active geological history, shedding light on the planet's transition from a warm, wet environment to the cold desert we see today. On the Moon, ancient volcanic activity created the dark maria that dominate its surface, offering clues about the Moon's thermal evolution and its relationship with Earth. Even small bodies like Ceres and Pluto reveal how volcanic processes, whether involving molten rock or icy slurries, can persist in surprising ways, challenging our assumptions about the conditions necessary for geological activity. The study of volcanism extends beyond the solar system, offering insights into exoplanets and their potential for habitability. Observing volcanic activity on distant worlds, either through atmospheric signatures or direct imaging, could reveal important details about their geology, climate, and the presence of subsurface oceans. As telescopes and instruments become more advanced, the lessons learned from volcanic activity in our own solar system will serve as a foundation for understanding the dynamic processes shaping exoplanets and their potential to host life. Ultimately, volcanism is a universal process that bridges the diverse worlds of the solar system, from the scorching plains of Venus to the icy depths of Europa and Enceladus. Its ability to transform landscapes, influence atmospheres, and create environments conducive to life makes it a key area of study for planetary science and astrobiology. By exploring the volcanic processes on other worlds, we deepen our understanding of Earth's own history and the broader mechanisms that govern planetary evolution. In doing so, we uncover not just the geological stories of individual planets and moons, but the shared dynamics that connect them as part of a complex and interconnected solar system.